Thank you very much. I see we're going to talk about certified ethical hacking, and then we're going to talk about a technology adopted all over Wall Street, so make from that what you will. So thanks very much for inviting me along, of course, and especially putting me second, giving an Irishman at an open bar. That was a very brave decision. My name is Fintan Quill. I'm the Global Head of Sales Engineering at KX, but you can just drop the sales word from that, because I'm actually a computer programmer myself. KX, we exclusively hire technical people to do the sales, so my receding hairline also gives that away, I think, as well. So has anybody heard about KX or KDB Plus or Q before? Raise a hand. How many of you have used it? Even less. Okay, so this is going to be the only marketing slide, so hopefully this is good enough. We're a pretty small company. We're headquartered out of Palo Alto in California. We have offices throughout North America, Europe and Asia. I'm based in our New York office. We have a pretty large user community, not by the standards of a lot of the languages used here, but several thousands of users. In terms of the markets that we're involved in the financial markets, energy, pharmaceuticals, government, software companies embedding our product in their tools, and then telco and oil and gas. But predominantly we've been in the financial services market now for just over 20 years. And I'm going to discuss some about that, and I'm also going to do some demos and stuff later. So kind of what we're all talking about, I just thought of a funny slide up, this is the only funny slide, is basically streaming real-time and historical data, and just one system and one language that can kind of do all of this. And we're coming from the financial markets, as I say, which deals with huge volumes of data, and petabytes is pretty typical for many of our customers. But what I want to do is just start talking about KDB Plus. So that's the name of the database. It's an integrated columnar database and programming system. So we do both streaming real-time and historical data in the one platform. We have trial versions available. So we have a 32-bit version which you can go and you can download and use for free. And then we have a 64-bit commercially licensed version too. And there's no difference between the versions other than the addressability. So in terms of some of the features of KDB Plus, we use standard operating systems, so we have builds available for Windows, Mac, Linux, Solaris on Spark and Solaris on Intel. We run on commodity hardware, so pretty much anything from a Raspberry Pi up to large supercomputers and everything in between. And what we're all about essentially is in-database analytics. And what I mean by that is just bringing the analytics directly to the data, so not extracting it using SQL and then manipulating using Python or some other statistical tool. And we also have compression built in, and we have compression built in from 3 viewpoints. And we can do compression over IPC, so if you're sending data from one queue process on one machine over the network to another queue process, we'll compress it before sending it across. And we also do on-disk compression as well, so if you've got large volumes of historical data, you can compress that down to a small percentage. And then we also do WebSockets compression as well, and I'll discuss that a little bit later when I go into the interfaces, etc. And we also have, yeah, question?
Just a suggestion that you hold the mic
a little further away. Is that better?
It's kind of clipping a little.
Cool. Yeah, can you hear me anyway?
Yep.
I'm a loud enough speaker, so. Cool. So then next is parallelism. So essentially with KDB Plus, we'll see an example of the parallelism a little later. And essentially you get it for free. It's kind of all built under the hood. You only have to know a few keywords. It's not a very heavy, complex multi-threaded API. We try and abstract that away from the end user as much as possible. In terms of language support, we have the following officially supported APIs. So C#, C++, Java, JavaScript, and R. And then there's community language supported APIs as well, so Python, Scala, Node.js, PHP, and Erlang. We also have interfaces available for ODBC, JDBC, and we have an inbuilt HTTP and WebSocket server. And the executable itself is just a few hundred kilobytes in size, so typically fits inside your cache. So this is a typical sample architecture. And as my colleague Kevin earlier pointed out, we've kind of flipped it upside down. We've put the application on the bottom and the actual back end on the top. But you'll see why. So at the bottom you got your applications here, and then at the top is kind of the overall view of the system itself. So this is quite similar to what you see a lot nowadays, a Lambda architecture. And we've kind of been doing it for 20 years, so it's not new to us. So typically you got your data coming in here. So your data could be coming from any sort of source. Financial markets, it could be coming from a market data feed handler. It could be coming from a smart meter data stream or clickstream data, and then it goes into what we call the KDB Plus events engine. So all of these processes here, and even these historical processes, they're all either KDB Plus processes or files and folders. And they're all written in the Q language, so there's nothing like specific that's different about these in terms of the actual kind of architecture of them. It's just the code is different. And what the events engine does is, as the data comes in, and it typically comes in over like a TCP/IP socket connection. And what the first thing it does is it pushes the data down to a transaction log file, which resides on disk. And typically you're going to have that running on a very, very fast local disk or like solid state drive, so that then if any of these downstream in-memory processes go down for whatever reason, you can replay the data very, very fast from this log file to get full recovery. And the simplest example then, the way the events engine works is it's essentially a data distribution engine or a complex event processing engine. And the simplest example of a subscriber to the events engine would be the real-time database. And essentially what that does is it basically just subscribes for everything. So it's a massive fire hose. And in many ways it's a bit of a dumb process, because all it does is it just takes the data and inserts it into in-memory tables, takes the data, inserts it, etc., etc. So it's not too CPU intensive, but it can be quite memory intensive, as obviously that gets larger and larger throughout the day or whatever way you've got your period set up. But then you can have like more specific engines as well. So you might have a streaming query engine, and that might be doing something like, say, subscribing for a specific topic, say for maybe like trade data, and then it might calculate, say, something like the average price for a specific bucket of symbols, stock symbols, or it might be subscribing for a specific, say, event in a clickstream engine, and then doing specific calculations. So what it will do is it will do the calculations even before it tabulates the data. So it means then you get really, really fast performance. And you can set up many of these streaming query engines, and all of the communication under the hood is just running over TCP/IP sockets. So as you see, these processes then, they might be slightly more CPU intensive because they're maybe doing calculations on the fly as the data comes in. But they're going to be way less memory intensive, because if you can compare that to the real-time database that's just constantly growing, essentially. And then what happens is typically at end of day or whatever pre-configured interval you want. So say for our financial markets customers, what they want is they want to hit the data coming in today and have it hot in memory, so they get really, really fast performance. So then typically at end of day, what we do is we then dump the data down to the historical database, which is on disk, of course. And typically what we do is we partition it or shard it, so for each day you get one particular partition or shard. But you can configure this, as I say. I mean, some customers, it's essentially a function of the size of your RAM and your machine. If you can fit a week's worth of data in RAM, then go for it, then purge it down every once a week or whatever. And so then the historical database would contain everything kind of like but today's data or but this week's data. But the nice thing about the KDB Plus historical database is it's all just standard files and folders on disks. There's no like specific weird format or anything like that. So for backup purposes, you can just copy it using like rsync or any like standard backup file folder backup tools like that. Or else you can have it running on something like a SAN or a NAS, and then you can have another process pointing at it from there. But the nice thing about the historical database is as well is that it can take advantage of the operating system file cache. So say if you go back and you query like yesterday's data or last week's data, and then you go back and you hit it again, you'll get typically in-memory performance. And that's all kind of abstracted away from the end user. You don't have to control the cache. KDB Plus does that for you. And then at the bottom here, of course, you can have your applications and your APIs, and they can communicate over standard pub sub, so they could subscribe directly to the events engine themselves, or they could also just do standard, query result. Are there any questions on that architecture diagram? Yeah?
Can you comment a little bit about consistency models and transactions?
Yeah. So in terms of the transaction model here, we don't have ACID transactions, and we don't pretend to be ACID transactions, because on the types of performance systems that we're working on, when you're talking about millions of messages per second, we typically don't want to do that, because people don't care whether the transactions are gone a minute later or not. And typically in financial markets, what you do is, because this is a time series database as well, is we just keep everything, essentially. So you can we even like keep the cancels and corrections as well, and maybe we apply it after the fact, perhaps in a sort of a batch style processing engine.
So you wouldn't get classical database referential integrity guarantees?
No, exactly. Yeah. But also one thing to note, actually, that I didn't mention earlier, is when the data is coming in, that the input queue is typically single threaded as well. So that's one way we kind of get over a lot of this contention issues as well. Yeah. Any other questions? Yeah.
I'm sorry, may I miss? Is there a data type on what kind of data you can send?
We have various different data types. I'll actually come on to that in a few minutes. Yeah. Any other questions? Yeah.
Does it work in a clustered environment, or is it a single host?
It can do either. I mean, typically most of our large financial customers will run it on a large memory machine, so you might have something like a 6 terabytes or 12 terabytes of RAM, but you know, we've seen it run over multiple machines as well, and you can have the historical database that can be spread over multiple disks, and so you can have a tiered storage architecture, so you might have maybe your last like weeks or months worth of data running on a solid state drive, and then you can have your older data then compressed on a, you know, a standard SAN or NFS file or something like that. And you can also have the historical database spread out over multiple machines as well, and then it will do all of the IPC protocol under the hood for you, so you could have it set up shared all or shared nothing. Yeah. Any other questions? Okay. So then on top of KDB Plus, we have our own programming language called Q. And what comes with the Q language? So it's essentially, it's SQL-like, so you can think of it as SQL with extensions. And we'll see it in action in a couple of minutes. And we also have native time series support. So to go back to the previous question about the data types, we have enhanced support for time series features. And so we have nanosecond timestamping, and I'll allude to that a little later when we start looking into the data model. And then we also have functional language features as well. So there's a lot of inbuilt functions, over 200 functions built into the programming language. But you can also create your own functions as well. And you can also load in C and C++ shared objects into the KDB Plus executable as well. So if you've got like some Fortran or C++ libraries that you want to load in, just throw them in. Similarly, if you've got stuff like written in CUDA and stuff like that, you can also load them in as shared objects and offload it. So this is a typical sample Q query here. So for those of you familiar with SQL, it's not too much of a jump in terms of syntax. We just have the initialization operator here, or the assignment operator rather, is the colon. So if you're coming from SQL, you probably think first price as open. We just do it this way. And as you can see, we have these keywords. So first, max, min, and last. They're all just keywords built into the Q language itself. And there's many, many aggregate functions that are available out of box. And we have this, what we call a symbol data type as well. So you'll notice we have this backtick AAPL. So that's just a specific data type in the Q language. I won't go into that too much there. Are there any questions on the query? No? It's not too difficult. So then in terms of comparing Q versus standard SQL, so Q does have the concept of order, which helps a lot for faster execution, and both in terms of joining data as well. So for that reason then Q eliminates many, many joins. And we support all of the standard SQL joins, but we also have extra joins as well, which I'll discuss a little bit later. And you compare that to standard SQL, which doesn't enforce row order. And the Q language as well, we also have built-in support for CSV and JSON and XML, so you can ingest the data in those formats, or you can also save it down in those formats very, very easily. So we hope, as you'll see with some of these queries a little later, that this leads to like higher productivity and less maintenance, as you just have less code to maintain, and you can debug it very, very easily. So this is just a sample. Q query versus SQL query. So this is the TPC-H benchmark and query 8. And as you can see, what KDB Plus does is we have the idea of foreign keys or linked columns, where we can basically link the columns under the hood to the other previous table. And so this is running over like 4 tables, I believe. We just use this dot notation to refer back to the other table, rather than creating this mess that SQL is here. So are there any questions on that query? Pardon? I know, yeah. I have another example of that as well, but we just put this one together today because we wanted to do something that was non-finance. I tried to put in as non-finance slides as possible. But I'll send this on so everybody will be able to see it. So just wanted to show the amount of code you needed to do it in SQL, basically. And then in terms of doing parallel queries or parallel calculations in Q, this is literally the serial version and this is the parallel version. So you have a function, say calculate event, and then you're calling it for a list of event types perhaps. So this is the serialized version where you're using the adverb each. So you do calculate events, each event types. And to parallelize it, you just use the keyword peach, which is parallel each. So that's our multi-threaded API. And this works over, we can do multi-threading and we can also do multi-processing as well. And it uses the same keyword, so you just set up your database with a number of slave threads or a number of slave processes, and it will be able to do that automatically under the hood. So as I say, it's not a heavy, concurrent API that you have to program. It's pretty simple and pretty lightweight. So then in terms of time series analytics is really one of the big things that we're at. So we have native temporal data types. So as I said earlier, we have nanosecond timestamps, we have millisecond timestamps, we have date, month, year, second, and hour. And these are all like first-class data types built into the Q programming language. And then you can cast between these data types very, very easily. So say if you've got your data stored down to nanosecond precision, but maybe you want to convert it to like 5-minute buckets or something like that, that can all be done on the fly rather than say storing it in two different cardinalities. And we also have the ability to do temporal arithmetic, which a lot of databases don't seem to have the concept of. So as I say, you can bucket the data, bar the data. You can add 5 minutes to every timestamp if you want to do windowing and stuff like that. And we also have as of join or bitemporal joins, as it's known, and that's when you're joining two different time series data sets, especially when the two events mightn't be aligned, but you want to get it as of a given time. And we'll see an example of that a little later. And we have the ability as well to join time series on the fly. So as I say, when the data is just coming in on flight, even before you tabulate it, you can join the two data sets together. So this is the kind of time series analysis continued. So in this particular example here, we're just querying data from an events table. We're just doing a select count I, so that's the equivalent of doing a count star in SQL. And then we're grouping it and aggregating it. Grouping and ordering, and we just move it inside the where clause, or the select statement itself. So then we're doing it by user agent, and then the data in the database is stored down to millisecond precision. So to convert it to the minute data type, we just do time.minute. And then we've got this xbar function which does the bucketing. And so if we do 5 xbar time.minute, it gives us the data in 5-minute bars or 5-minute buckets. And then we're doing it where the date within .z.d is just a shorthand for doing the current day, and then do -7, so 7 days ago, so the last week, and today. And so this is simply where you do it. So this is the equivalent of doing between today -7 and today, and then the event type equals login. And then at the bottom here is the example of the as of join that I mentioned earlier. So this is this bitemporal join. And so if you think of a typical example in the financial markets is somebody might be quoting, say, I'll buy Microsoft stock for this price and I'll sell it for this price, and then somebody will buy it. So I might be quoted, say, Microsoft at 10 a.m. and then for simplicity's sake, I might buy it till 10:01. So then when you try and join those two data sets, typically because they have two mismatched timestamps, you won't be able to do it using a standard SQL join. And so what this as of join here does is it's a function, AJ, for as of join, and it takes 3 parameters. The first parameter is the time, which is the column that we're actually going to join the data sets on. And then the second parameter rather is a table that we're going to look up from. So what we're doing here is we're selecting our time and our price from the trade table, where the date is the last date in the database and the symbol equals Microsoft. So we're going for yesterday's data, picking off Microsoft data, and we're doing a select the time and the price. So this will be the trade price, the price that we actually bought the stock for. And then the final parameter then is a table that we're going to look up into. So we're selecting the time, the bid and the ask, which is somebody's willing to buy or sell it to us at, from the quote table, where the date is the last date and the symbol equals Microsoft. So then what will happen then under the hood is our trade data, remember we bought the stock at 10:01, it will look into the quote table and it will say, well, what was the price at 10:01 being quoted? And it will see, okay, there's no value at 10:01. So then what it does is it looks back in time, it does a binary search essentially, and it will find the last available record. So are there any questions on that syntax? For those of you coming from a functional programming and SQL, this shouldn't be too difficult. Yeah, the syntax is just, it takes a little bit of time to get used to like anything, but I think the general idea is that a lot of this stuff comes out of box rather than a lot of other databases out there. And there's also a generalized version of as of join as well called a window join, where you can specify a parameter a window as an extra parameter, and then it will say do something like what will happen 1 second before an event and 2 seconds after event. So then you can do say stuff like market impact analysis in the financial markets, or just start doing latency monitoring as well if you're doing like really high speed systems. And then this is just a simple example as well of just Q versus Hive ETL. So as I said, Q is also kind of a functional programming language as well. I mean, it's not purely functional like Haskell and stuff like that, but you can see the kind of general idea here. So this is basically loading data in from a text file and then saving it down to a table. And then this is the Hive equivalent, and we've actually got this ratified by a Hive expert. So as you can see, it's pretty productive here. All we're saying is on the right hand side here, this is the file that we're going to read in. We read it in using this function, and this will be the data type. So we're going to have an integer, the symbol data type, a floating point, and a symbol data type, so 4 fields, and then it's going to be comma separated. We load that in, and then we just save it down to a file on disk called product.dtl. And then this is the equivalent in Hive. So with very little code, it can be very productive, and it's also extremely fast as well. So now I've got the demo, so I'll move over to my other machine. So I'm gonna show a few different queries here. So I got this file earlier today. This is one I prepared earlier, as I say. And it's about 1.6 gigabytes in size. Oh, yeah, sure. Okay. Is that a bit better? I mean, this is just kind of like a nonsense text file. The queries will be more interesting. You see that now? Kind of. You get the general idea though, that it's basically, this is just like a sample kind of like log file, and I'm just trying to show the general format of it. So it's like a pipe delimited file. You see there are several different fields here, so event ID, timestamp, event name, user ID, etc. And then there's like a payload at the end. And for the queries we're using though, we're only going to extract a few of these fields. And these are the queries we're actually going to run. So what I'll do is I'll actually run this file now. So we have our script here. And I'll just let it run. It takes, I think, about 12 seconds to load in the file. No, it's even faster now.
This is bringing it into the real-time database?
Yeah, it's bringing it into memory, yeah. So you can load data in via files as well. So like CSVs, you don't have to put it in over TCP/IP necessarily either. Okay.
So what's this now?
Yeah. So these are the queries essentially that I'm running. So this is a loading code at the top here. Can everybody see that okay? Or should I increase the font size? Okay. So what we're loading is we're loading in this file, we're extracting the fields that we care about. We're loading in a timestamp field, a user ID field, and an event name field as symbol data types, and then we're just deleting the first row, so where I equals 0, because there was an extra kind of line in the header. And the /ts in front of it does the time and the space used, so it does the time in milliseconds and the space in bytes. And then all I'm doing here in this third row is I'm just ordering the data by these 3 columns: user ID, timestamp, and event name. So then what the first example here is doing is we're actually trying to get basically when a user signs up, when do they start to buy something, and at what time did that occur, and then at that point when did they refer a friend to join. And it's just done in just a few lines of code here, and then we have a standard inner join here as well that we call. And as I'll say, I'll send on some of this code as well. The second example then, we're getting the revenue, so did somebody buy something, and then if they did buy something, did they sign a friend along? And I'll send on more information about this as well. And then we're using this window join function here, the WJ1, which I mentioned earlier when we had the as of join and the window join. And then there's another query down here where we're basically grouping the data based on revenue type by user ID. So you see this idea of doing something by a field from T. And then I'm just showing it here. So that means I saved it down to this temporary table, Q3, and then I'm just showing it, i.e. outputting it to the screen. But what I'll also do is I'll just start actually like creating some tables as well, just so you can kind of see the language in action. So you start off the Q executable, and you're running just in an interpreter. So there's a queue interpreter. Start it off. What I'm going to do is I'm going to create a table T. I'm going to have an unkeyed table. I'm going to create 2 columns, A equals 1, 2, and 3. And because it's a vector columnar-based language, you can create the tables really easily and make them out of lists and vectors. Okay, so there you go. We got our table T. And then we can use a function flip the table T to get a dictionary. So then all of a sudden it turns into the dictionary, so key value pairs. And you can run a select-like statement on it. Select A from T. You get your result back, or you could do select, maximum A from T. So you can see where you can start creating these complex data sets very, very easily. Just all running them on the interpreter as well. So what I'm going to do now is I'm actually going to go to a data set that we have running on our server in our office. So this is about 256 gigabytes of RAM. And the data set that we're loading is New York Stock Exchange trade and quote data. So it's a pretty large data set. It's about 14 terabytes in size altogether. So the main table that we have here is the quote table, which has about 354 billion records, as you see. And we also have a trade table, which has slightly less, because it's about a 15 to 18 to 1 ratio between trades and quotes. So I see. Should take a second.
Is this running off that real-time database or the historical?
This is all historical data. Yeah. So this is all on this data. There we go. So it's about 16 billion records of trades. And if you see, you can see the meta of the data as well. So you see, they're relatively small records. They're not like huge records. So you've got a date, a symbol, a time, a bid, and ask, a bid size, and ask size, and then mode and exchange. You don't really have to know what they mean. And then you see the data types here as well. So there's the date data type, the symbol, and the time data type, the 32-bit floating point, integer, character. Okay, so what I could do is I could do something like, say, I'm gonna save this to a temporary table T. So I'm going to do /ts, which I said is this time and space, so the time in milliseconds and the space used in bytes. And I'm going to calculate the volume weighted average price. So size weighted average price, and by symbol from trade, where date equals the last date. Can you see that? On the small. Okay. And then I'll run this. Just have to increase the font size. Is that better? Cool. Sorry about that. So I'm basically doing this over all of the records for a specific date in the database. So for every single stock symbol, which there's several thousand, and we're calculating the volume weighted average price. And this is the message by message data, so this isn't any pre-aggregated data or anything like that. So we're scanning, as you see, several billion records. So we run that now. There we go, 409 milliseconds. And then if you want to see the results, just so you can believe me, here is count of T. 8,000 symbols we've managed to aggregate over. So what we could do is go back to the query and we'll just get the count I. So you see how many records that we ran over. And this is all just run off one machine. There's no SSDs on this machine, it's all standard spinning disk. And we have 2 LUNs. As you can see, it's about 25 million records we've aggregated over in less than half a second. Any questions on that?
That seems faster than memory bandwidth.
Well, I guess the way it works under the hood is we're only, it's all files and folders on disk, so maybe that's what we'll do next, is I'll actually go to the demo page here and I'll show you kind of the directory layout. So this is what this layout kind of looks like on disk, essentially. So the way you save data down is dependent on the size of the tables, essentially. So you might have a root folder here, the database folder, and then you might have, if you have very, very small tables, and that will fit comfortably in memory, what you can do is you can save them down to disk serialized in one file. And then if you have maybe slightly larger tables, like summary data, that might just be on the brink of memory size, what you can do is a technique called splaying. And by splaying, it means that the table name is the folder name, and then every column within the table is one specific file on disk. And then if you've got larger data sets, such as like massive daily data, like time series tick by tick data, or maybe like smart meter data, then you can save that down in a partition. So the real-time database will push its data down to disk. It will create a new folder, which is the actual date, and then within that folder we'll have a folder for each table, and then within that again it will have a file for each individual column. And where you really get the speed and performance of KDB Plus on disk is via this file and folder structure. So saving it down in these different ways is just a function call. So you as the end user, you don't have to go in and do make dir, touch file, etc., etc., etc. You just have to know the 3 function signatures to save the data down in this different way. So essentially with the query that we were running, we were basically doing it for one date in the database, and we were calculating the volume weighted average price. So for that, all we needed was 3 columns. We needed the symbol, the price, and the size. So what KDB Plus under the hood will do is it will go into this particular folder. It won't bother with any other folder. It will just go into the date folder in question. And what it does is it memory maps the files. So it will memory map symbol, price, and size. And then typically what we do with the time series data is before we purge it down to disk is we reorder it by the field that we're going to aggregate on. And in financial time series, it's typically the stock ticker, because you want to do average prices for a specific stock. So that means then within this partition, the data will be ordered by symbol and then by time. So it means then if we're doing it for Microsoft, all of our Microsoft data is held contiguously into one file. So if we're just doing a volume weighted average price for Microsoft stock, what it will do is, as I said, it will memory map these 3 files, but then it will only physically read in the segments of those files that correspond to Microsoft. Then the data is fully in memory and it runs the query. So it means then, you compare it to the SQL where you basically have to read in the full record, so it might be like 7 or 8 fields, even though you only care about 3 of them. And then also as well, because the data is not held sequentially, it means your disk head is physically going to be skipping all over the place. Whereas with us here, all you're doing is 3 sequential disk seeks, so it's exceptionally fast. There's very little I/O. You just take advantage of the disk as much as possible, and then you just have all of your data in memory that you really, really want. So what it really does under the hood is it really just zones in on the data that you actually care about, rather than scanning a lot of data unnecessarily. So are there any questions on that?
Can you go back to the query that you
Yeah. This query, was it? The weighted average query, was it?
weighted average is by symbol.
Yeah.
So for each symbol, it's computing weighted average.
Yeah.
Okay. So that actually examines every price for
Yeah.
every symbol?
Yeah, that's right, yeah. And for that particular date, remember, so we're really,
What's the cardinality for that day?
It was 25 million records. Yeah.
That's a very different fact.
Yeah.
There was one before.
We're good, but we're not that good.
There was one before that where you had like several billion records that you.
that was the quote table, yeah. Yeah.
And that ran in 400 and something milliseconds, 409 milliseconds.
No, that was the volume weighted average price one on the trade table that we ran, yeah. So to just give you an idea of, what I can do is I can show you what the records look like. I can just do 10 take. That just returns the first 10 rows, so we just do 10 take, so the hash key means take. And this is what the records look like, so you got basically whatever, like, I think it's 16 billion trades, and this is kind of the format of it, so it's very, very structured data. So are there any questions on those queries? Anyone senior? Pardon?
What is the count of the trade?
What was the count of the trade table was about 16 billion records, and then the quote table has about 354 billion records. Yeah.
How do you deal?
Comparisons between the IO, CPU, and other things. Just play one of them.
And this particular database is running on one core. We didn't set it up to run on multiple cores. I could probably change, and I could run it a bit faster as well. Yeah.
How many machines do you run off?
This is just one machine. Yeah.
How many can you run off? Or how many
You can run on, you know, as many machines as you want. Essentially, kind of we just scale pretty easily, horizontally and vertically. Yeah. So you could have this. You could have, you know, that historical database kind of layout that I mentioned earlier. You could have that, you know, running over multiple machines, either in shared all or shared nothing mode. Yeah.
How do you federate the query across those and bring the aggregates?
Yeah, it's all done under the hood. So it's not every type of query pattern. So what we do is we basically do a map reduce under the hood, but it's not like Hadoop map reduce, you know, because they think they invented it, but they didn't. It's been around forever. So yeah, we have our own kind of like map reduce first. So for specific query patterns, we'll recognize, okay, is this easily parallelizable? And it will base it based on where the disk is located as well. So, you know, conserve locality. It won't try and send as much data over the wire. So it'll be stuff like an aggregation. Like in that case where we saw with the volume weighted average price, what you'll see is that like maybe each process will get its own like stock ticker symbol to work over, pull the data and only work in it for that. And similarly, this will scale over multi-cores as well. So if you're just on one big machine, you could have that same calculation, say, pre-allocate, you know, a stock to each particular core to work on that as well. And there's pretty much linear scaling. And in the last few years, we've put in multi-process handling as well, and so we can run over multiple machines, but also run even multi-processes on the one host. And we typically find it gives much better performance than multi-threading because you don't have any like lock contention or anything like that. You can just let all of the several slave processes just work on each individual item itself.
What about variable size fields instead of all fixed size fields?
Yeah, you can store nested data as well. I mean, typically, you know, for really large data sets like these where you've got billions and billions of records, you typically don't want to do that as much as possible. If you can avoid that, that would be great. But yeah, we've got no problem, you know, supporting it, but just the performance won't be as good. But yeah, you can certainly do nested data as well, and that's typically what a lot of people will do. They might, like, you know, work on this large flat data set, and then they'll, you know, aggregate it down to a more nested data structure that's more manageable in memory. Yeah. Any other questions? Yeah.
What kind of throughput do you see on high frequency trading or North America trading markets during the day usually? How many million queries per second? Really? How many million rows per second?
Yeah, how many million rows per second? I actually have a slide on that, so I'll go back. And that was the demo. So in terms of the summary, this is kind of, as I mentioned earlier, we can scale to multi-petabyte solutions and multi-machine. And then in terms of the throughput, these are the sort of figures we typically see in like a standard like Intel CPU. So you're talking about 1 to 2 million single inserts per second per core. I mean, those are, you know, relatively sized inserts. So like the records that I was talking about here, where maybe you've got 7 or 8 fields of, you know, reasonable enough size. You're not talking about massive records. And then typically when you do bulk insertions, then you'll get typically an order of magnitude better performance. And the reason for that being is that it's basically one mem copy per column. So if you start bulking up the data, because it's already a vectorized solution, one mem copy per column, whether you got like 6 or 7 columns, you can kind of get this order of magnitude performance. And, you know, it's actually probably even better. I mean, in certain calculations that I've done, you can get about 15 to 20 times performance if you start bulk inserting instead.
Is this just memory commit time? I mean, what happens if you exceed the memory buffer?
Oh yeah, this is just memory commit time. So if you were sending it in over like TCP/IP or something like that, yeah. Yeah, in terms of like saving it down to disk, you really have to be behest of your disk controller essentially. Yeah. And then, you know, at the end here is just the faster development time with a, you know, a very efficient programming language. We think that, you know, the turnaround time really comes down. You typically need less developers. And then, as I mentioned earlier, you typically need a less hardware infrastructure. It's very, very efficient with the hardware. As I said, the memory footprint is extremely low, because we try and load as little data as possible into memory, and only the data that we really, really care about. So typically, you know, with a lot of our financial clients, they'll just use one reasonable size memory machine, rather than running on, you know, a cluster of smaller machines, because typically, you know, the biggest bottleneck is going to be network. So eliminate the network, and that's pretty much about it. There's a few resources here, so you'll see a lot of these links on the follow-up slides. So we've got the free version that I mentioned, the 32-bit version, which is being used by a high-profile company in the Seattle area very successfully. And we also have a wiki page as well, where we have like a description of all of the functions in the language. We have a community page, we have a Google group, we have a GitHub page where you'll find a lot of those resources. You know, there's a lot of projects, there's frameworks built on top of KDB+, so you've got a more like application kind of stack built out of box. And there's a book as well called Q-Tips, which is available on Amazon, which is based around, it teaches the Q language, but in the context of an actual system, a financial system that's being built in it. And then there's also a very interesting link if you're very hardware savvy, called the Stack Benchmarks. So this is the Securities Technology Analysis Center. What they do is they do financial technology benchmarks, and they do very, very real world calculations. So the benchmarks are actually kind of written by the banks themselves. So they say, okay, we don't want to run 20 POCs against 20 databases, so you guys do this for us. So the benchmark in question, it runs 17 different analytic tests. So just stuff like the ones that I did already. So calculate the volume weighted average price for X number of stocks over Y number of months. And other such examples like that. And it's run against databases of different size. So 1 terabyte, 10 terabyte, and I think it's a 100 terabyte data set. And it's all independently verified as well. So they have the machines in their lab, and they actually run the software all themselves. And it's the benchmarks, they run against a variety of different hardware solutions. So you might have the newer generation Intel chips, AMD chips, even like CUDA chips, and then also you got different setups as well, so different RAM sizes or different disk solutions, whether you're using solid state drives or non-volatile DIMMs or DRAM SSDs, and then just running it off standard disk, and then different file systems as well. So you got XFS, ZFS, and Lustre file system, which a benchmark just came out today running on the parallel file system. And then we have meetups as well. So we have meetups in pretty much every major city in the world at this point, including Seattle. So we'll have more of those meetups. And thank you very much. We have our Twitter handle here. And my Twitter handle is my name, @Fintan Quill. If you have any questions, just feel free to ask now or later or whatever. Thank you very much.
There's a quick confirmation. Your performance of 25 million records in sub-second time response, that's like under a microsecond per record. That has to be leveraging the file system, caching system of the file, right?
Yeah. Not necessarily, yeah. I mean, the query that I ran probably did, yeah.
Okay, so that's a quick confirmation. The other main question is that I'm not expert in this, but I have seen there's a open source platform called Esper. That's the
yeah.
So you can comment on that. I'm not expert, but I want to hear you elaborate it and compare to that open source platform and your system. Yeah.
I don't know much about that.
Could you repeat the question?
Oh yeah, he was wanting to compare KDB Plus with Esper, and I've heard of it, but I don't know that much about it to be able to comment with any kind of level of authority. My apologies.
How far can I go with your free trial version?
Well, it's limited to the 32-bit address space, but as I say, you could set up multiple processes running the 32-bit and have them communicating with each other as well. So you got the limit of 4 gigabytes worth of data to suck into memory, but you could have a massive database on disk just as long as you're not pushing more than 4 gigabytes of data into memory. So there's interesting people in interesting cities like Seattle doing interesting things with the 32-bit version as well. But it's got, in terms of the functionality of the language, it's got all of the syntax is exactly the same. There's no difference, and there's no extra things going on. So in terms of like doing stuff like those as-of joins, there's nothing limited there. Literally just a memory space limitation. That's
so
it.
Just ballpark, what's that threshold for not fall over and have to buy your software?
Oh, okay, yeah, we license it for processor core basis. I mean, we can chat about the licensing. Well, we see that's why we mentioned the lower cost of ownership argument, because sometimes there's open source that isn't very performant, and you can pay 10 developers like $250,000 a year when you can buy a nice database for a couple of grand. Diplomat. Yeah, it's a few grand. Yeah. Oh yeah. And as I said, that query there that I was running is just running on one core as well. So a lot of the time, you could take advantage of all of the cores if you wanted as well, or you could take advantage of just one core, depending on how parallelizable your query is, of course.
So that database you were doing, what was the cardinality of that last state? The number of events?
So the trade table altogether was 16 billion records.
Yeah, but you were focused on the last state.
Oh yeah. That was.
So what was the cardinality of records in the trade table?
It's about 10. I think it was like 16 million or 10 million. Or is it 25 million? I think it was. Yeah, something like that.
25.
Yeah, million. Yeah.
All right.
Yeah.
So you showed that you can write at least some of the PPC queries.
Yeah.
Did you actually run any of the PPC benchmarks? Have any like cost performance figures?
Yeah, don't have anything like cost per performance figures. We do have the whole TPCH benchmark written out as well. I could actually, add a link to that if you were interested as well. Yeah, and it's actually all in just one page, so it's not very clunky. Any other questions?
I have a question here.
Yeah.
So you did query and setting up table. If I ever a client, I want to start using your streaming service.
Yeah.
And I want to have a new kind of records. And how do I have to have some kind of development time, or I can have interface or a service to define dynamically the record I want to track, and then be able to query and then do the
Yeah, I mean you can send it over IPC to push the message in, or as I said, you could load it from like a CSV file, which we saw with the event data that we were loading in as well. So you can do it either way. I could even just, if you want me to run a quick example, I'll just open 2 windows. Am I running over time here? Is this okay? Cool. Okay, so what I'll do is, this is our data that we set up, the database table. I'll set it running on port 9999, and then I'll go into another window. So that's just the /p command sets it listening on a TCP IP host and port. And then I can go into another, I'll just increase the font size here, sorry. Okay, so this is just a raw queue process. It's not listening or anything like that. And what I'll do is I'll create, connection handle, and then I'll do a hopen, and I'll do backtick : 9999. You don't really have to understand the syntax, but basically what this is doing is creating a connection. So it's doing a connection open a handle. Okay, so that's literally just a file descriptor. So an integer is actually a function in the Q language. So it's just a file descriptor, a socket descriptor under hood, and we can do say con, and then say select from T. Then we get the data back, so we're pulling it over from the other process. So if we type T here, we don't get anything, it just gives us an error, we don't have a table T here. So you can do that communication. You can also do it asynchronously as well. So we've got a full communication stack, we've got HTTP support and also WebSocket support. And we can work as a WebSocket server and as a WebSocket client as well. So we have a lot of people now that are doing Bitcoin mining, because WebSockets is essentially the protocol that's being used all over Bitcoin mining. So they can do the full stack using KDB+. So just a few hundred kilobytes, you get a database, a programming language, a HTTP server, and a WebSocket, fully compliant WebSocket server as well. We pass all of the out-of-band tests that are defined in the WebSocket standard. Any other questions? No.
Time for a beer?
Yeah.
Okay, thanks very much to our both our speakers, to Eric and to
Fintan.
Thank you.